What if I told you there's this state of matter where electricity flows with absolutely zero resistance?
Zero resistance.
None,
Yeah.
no friction, no loss of energy, just pure effortless flow.
Hmm.
Sounds kind of sci-fi, right?
It does sound futuristic, yeah, but it's a very real phenomenon. It's called superconductivity. And what's even wilder is that it was discovered over a century ago,
Wow.
back in 1911.
So 1911,
Yeah.
quantum mechanics was still in its infancy.
Right.
What led to this groundbreaking discovery?
Well, it all started with a Dutch physicist.
Yeah.
His name was Heike Kamerlingh Ons, and he was obsessed with the pushing the boundaries of low-temperature physics.
Okay.
He was the first to liquefy helium,
Wow.
which allowed him to reach temperatures just a few degrees above absolute zero.
So he had this powerful tool to explore, like this uncharted territory of extreme cold.
Yeah.
What did he do with it?
Onston decided to investigate how electrical resistance behaved in materials at these ultra-low temperatures.
Okay.
He started with mercury, a good conductor even at room temperature. The prevailing theory at the time suggested that as the temperature decreased, resistance would gradually decrease and eventually plateau.
That makes sense, right? You're
Yeah.
slowing down the chaotic movement of the electrons,
Yeah.
making it easier for them to flow.
Right.
But that's not what happened, is it?
No, it wasn't.
What happened?
As Owens cooled the mercury down to around 4.2 Kelvin, something truly astonishing occurred.
Ah.
The electrical resistance completely vanished.
Or the...
Gone. Poof. It was as if the mercury had entered a completely different state.
Wow.
One where electricity could flow without any hindrance whatsoever.
That must have been a mind-blowing moment.
Oh, absolutely.
Imagine witnessing that in the lab.
Yeah.
Did Owens have any idea what he had stumbled upon?
He knew it was something extraordinary, something that defied the classical understanding of physics. He called it superconductivity, but the underlying mechanism remained a mystery for decades.
They had this incredible phenomenon,
Right.
but they had no clue how it worked.
Exactly.
That must have been frustrating for the scientists.
It was, but it also fueled a firestorm of research. Physicists were determined to unravel the secrets of superconductivity,
Yeah.
and it ultimately led to the development of a whole new branch of physics, quantum mechanics.
Okay, so quantum mechanics comes to the rescue.
Yes.
How did this new way of thinking about the world help explain superconductivity?
It took some time, but in 1957, three physicists, John Bardeen, Leon Cooper, and John Schrieffer, developed a theory
Okay.
that finally explained the microscopic mechanism behind conventional superconductivity.
Right.
Their theory, known as BCS theory,
BCS theory.
proposed that electrons in a superconductor form pairs called Cooper pairs.
Okay, Cooper pairs.
Yeah.
I've heard that term before, but
Yeah.
what are they exactly?
So imagine two electrons which normally repel each other,
Right.
forming a bound pair.
Ah.
This pairing occurs due to interactions with the vibrations of the material's crystal lattice. It's a bit like two dancers moving in perfect synchronization, gliding effortlessly across the dance floor.
I like that analogy.
Yeah.
So instead of individual electrons bumping and jostling their way through the material,
Right.
we have these gracefully paired electrons moving in perfect harmony.
Exactly.
That's a beautiful image.
It is.
So this elegant dance
Yeah,
is the key to zero resistance.
it is. These Cooper pairs, they condense into a single quantum state,
Okay.
behaving like a collective entity rather than individual particles.
Right.
And because they're all moving in sync, they don't scatter off impurities or imperfections in the material, which is what causes resistance in normal conductors.
That's fascinating.
Yeah.
So BCS theory provided a solid explanation for why conventional superconductors worked.
It did.
But there was still a catch, right?
Yeah.
These materials only exhibited superconductivity at extremely low temperatures.
You're absolutely right. Liquid helium, which was needed to reach these cryogenic temperatures, was expensive and difficult to handle. It was a major roadblock to practical applications.
So superconductivity was this incredible phenomenon with huge potential,
Absolutely.
but it was stuck in this ultra-cold world,
Yeah.
limiting its real-world usefulness.
Exactly. And that's where the story of superconductivity takes a dramatic turn.
Okay.
In the 1980s, with the discovery of a new class of materials that shattered the theoretical limitations of BCS theory.
Uh-oh.
Yeah. So we had BCS theory neatly explaining how conventional superconductors worked, but it had this temperature limitation.
Right.
It was like having a powerful engine that could only run in the Arctic.
Yeah, that's a great analogy.
But then, in 1986, two physicists at IBM,
Huh?
Carl Alexander Müller and Johannes Georg Bednorz, they made a discovery that sent shockwaves through the scientific community.
I'm on the edge of my seat. What did they find that was so groundbreaking?
They were experimenting with a class of materials that no one expected to exhibit superconductivity,
Okay.
ceramics.
Ceramics.
Specifically, they were working with a barium-lanthanum copper oxide compound, a type of material that was known to be a terrible conductor at room temperature.
Wait, ceramics, the stuff teacups are made of.
I know.
That doesn't sound very conductive at all.
It seems counterintuitive, but Mueller and Bednorz had a hunch that these ceramic oxides might hold hidden potential. They were intrigued by the unique electronic structures of these materials, and they decided to see what would happen if they cooled them down to extremely low temperatures.
So they were going against the conventional wisdom,
Yeah.
exploring this uncharted territory of ceramic materials.
That's right.
What happened next?
They hit the jackpot.
What?
They discovered that their ceramic compound exhibited superconductivity at a temperature of 35 Kelvin.
35 Kelvin.
It wasn't quite room temperature,
Right.
but it was significantly higher than anything BCS theory predicted.
Wow, 35 Kelvin. That was a huge leap forward.
It was.
What was the significance of this discovery?
Well, it was a game changer for several reasons. First, it shattered the theoretical limits that everyone had believed in BCS theory, couldn't fully explain how these ceramic materials called cuprates could superconduct at such relatively high temperatures.
It was like these cuprates were saying, hey, BCS theory, you're not the only game in town.
Exactly.
They were rewriting the rules of superconductivity.
Exactly. And second, this discovery opened up a whole new avenue of research, a global race to find new and better high-temperature superconductors.
Wow.
Scientists were suddenly exploring a vast and uncharted territory of materials,
Right.
driven by the dream of achieving superconductivity at even higher temperatures.
It was like a scientific gold rush.
Yeah.
Researchers all over the world scrambling to find that next breakthrough.
Absolutely.
What were some of the key developments that emerged from this frenzy of research?
Well, one of the most exciting breakthroughs was the discovery of cuprates that could superconduct above the boiling point of liquid nitrogen,
Okay.
which is 77 Kelvin.
77 Kelvin?
This was a major milestone because liquid nitrogen is much cheaper and more readily available than liquid helium.
That's huge.
Right.
It meant that superconductivity could potentially become more practical, less reliant on those expensive and finicky cryogenic coolants.
Right.
So were we suddenly on the cusp of a superconductor revolution?
Not quite. While these high-temperature cuprates were incredibly promising, they also presented some formidable challenges.
Like what?
Unlike metals, which are ductile and easy to shape, cuprates are brittle ceramics,
Huh.
prone to cracking and breaking.
That sounds like a major headache for engineers trying to build practical devices and applications.
Yeah.
Imagine trying to wire a power grid with superconducting cables that snap like dry spaghetti.
You hit the nail on the head. The brittleness of cuprates was a major obstacle to their widespread adoption.
Yeah.
But engineers are a resourceful bunch,
Sure.
and they weren't about to give up on this game-changing technology. They started developing innovative techniques to process and fabricate these temperamental materials.
So they were determined to tame these wild cuprates,
Yeah.
to find ways to make them more manageable and reliable.
That's exactly.
What kind of techniques did they come up with?
Well, they explored various approaches from thin films to coated conductors.
Okay.
They found ways to deposit thin layers of cuprates onto more durable substrates,
Right.
making them less prone to cracking.
Hmm.
They also developed techniques to improve the grain boundaries between these ceramic materials,
Okay.
reducing their brittleness.
It's like taking a fragile piece of pottery and reinforcing it with a network of tiny invisible fibers,
Yeah.
making it much stronger and more resilient.
That's a great analogy.
And while the engineers were busy tackling these fabrication challenges,
Right.
the theoretical physicists were hard at work trying to understand why these cuprates were behaving so differently from conventional superconductors.
Yes.
So BCS theory was still struggling to explain these high-temperature rebels.
Yeah.
What were some of the new theories that emerged to try and make sense of cuprate superconductivity?
Well, it turned out that the simple, elegant picture of Cooper pairs dancing gracefully in a uniform lattice didn't quite capture the complexity of what was happening in these layered ceramic materials.
Huh.
The electrons in cuprates were behaving in much more exotic ways,
Huh.
interacting with each other and with the lattice vibrations in ways that were difficult to model.
So it was like the choreography of the dance had become much more intricate and difficult to decipher.
Exactly.
Did scientists eventually crack the code of cuprate superconductivity?
Not completely. Despite decades of intense research, the mechanism behind high-temperature superconductivity in cuprates remains one of the biggest unsolved mysteries in condensed matter physics.
Wow.
There are many competing theories,
Right.
but no single theory has been able to fully explain all of the observed phenomena.
It's like having a puzzle with some of the pieces missing.
Yeah.
Tantalizingly close to a complete picture, but still shrouded in mystery.
Right.
So while the theoretical understanding of cuprates remained elusive, were there any practical applications that emerged from this research?
Yes, definitely. Despite the challenges of working with these brittle materials, engineers made significant progress in incorporating high-temperature superconductors into various devices and technologies.
Okay, let's talk about some of those real-world applications.
Sure.
Where did high-temperature superconductors start to make a tangible impact?
One of the most exciting areas was magnetic levitation, or maglev technology. Imagine trains gliding effortlessly above tracks at incredible speeds,
Good.
using superconducting magnets for levitation and propulsion.
Now that sounds like something straight out of a sci-fi movie.
It does.
Did these maglev trains ever make it past the prototype stage?
They did. Japan, in particular, has been at the forefront of maglev development, testing trains that have reached record-breaking speeds.
Wow.
But the cost and complexity of building these specialized tracks have been major hurdles to widespread adoption,
So it's more of a technological marvel than a practical mode of transportation.
at least for now.
Right. What about other applications?
Yeah,
Did high-temperature superconductors find their way into other fields?
absolutely. Another area where they showed tremendous promise was in power grids. Imagine transmitting electricity with virtually zero energy loss,
Wow.
making our energy systems incredibly efficient and sustainable.
Okay. That would be a game changer.
Right.
No more wasted energy, less reliance on fossil fuels, and a greener planet. Sign me up. Were there any successful experiments with superconducting power grids?
Yes. There were pilot projects demonstrated the feasibility of using high-temperature superconductors in power cables,
Okay.
showcasing their potential to revolutionize how we generate, transmit, and distribute electricity.
So we're talking about a technology that could transform our energy infrastructure,
Yeah,
leading to a more sustainable future.
absolutely.
But I'm guessing there were still some challenges to overcome.
You're right. Cost, scalability, and reliability were still major concerns.
Hmm.
Integrating these high-temperature superconductors into existing power grids was a complex and expensive undertaking.
It's like having a revolutionary new engine, but needing to redesign the entire car to accommodate
Yeah.
it. It's a massive engineering challenge.
Exactly. But despite these hurdles, the potential benefits of superconducting power grids were so compelling that research and development continued to push the boundaries of what was possible.
So we have maglev trains and power grids, both tantalizingly close to becoming a reality, thanks to high-temperature superconductors.
Yes.
Were there any other fields where these materials started to make their mark?
Yes. There was another area where high-temperature superconductors had a profound impact: medical imaging MRI machines, which use powerful magnets to create detailed images of the human body,
Okay.
rely on superconducting technology.
Okay, now we're talking about applications that have directly benefited countless lives.
Yeah.
How did high-temperature superconductors revolutionize MRI?
Well, traditional MRI machines used electromagnets,
Right.
which required huge amounts of energy and produced a lot of heat.
Yeah.
Superconducting magnets changed the game. They allowed for stronger, more stable magnetic fields,
Yep.
resulting in higher resolution images.
So it's like going from a blurry old photograph to a crystal clear high-definition picture.
Yeah.
That's a huge leap forward in medical diagnostics.
Exactly, and that's just one example. Superconducting technology is also used in other medical applications like magnetoencephalography, or MEG, which measures the magnetic fields produced by brain activity.
Wow. I'm starting to see that even though we weren't living in a superconductor-powered utopia, yet these materials were already having a significant impact on our lives, from transportation to energy to medicine. But the story doesn't end there, does it?
It doesn't.
The quest for even higher temperature superconductors, ideally at room temperature, continued.
You're absolutely right. That dream of achieving superconductivity with a need for any cooling never faded. And in the early 2000s, the field of superconductivity took another unexpected turn,
Uh-oh.
with the discovery of a new class of materials that challenged the prevailing wisdom once again.
Welcome back to our deep dive into the world of superconductivity.
Yeah.
We've explored the history, the breakthroughs, the challenges, and the remarkable applications. But there's one question that's been lingering in the air, like the scent of possibility. Can we achieve superconductivity at room temperature?
That is the holy grail of superconductivity
All
research,
right.
a dream that has driven scientists for decades.
Yeah.
And while it once seemed like a distant fantasy, recent discoveries have brought us closer than ever before.
So we're talking about the possibility of a world where superconductivity isn't confined to ultra-low temperatures.
Exactly.
A world where those incredible properties,
Right.
zero resistance, powerful magnetic fields,
Yeah,
are available at our fingertips.
that's the idea.
What's been the key to this renewed hope?
The answer lies in the realm of high-pressure physics.
High-pressure physics.
Yeah, imagine squeezing a material with unimaginable force millions of times greater than the pressure at sea level.
Wow.
This extreme pressure can fundamentally alter the material's properties,
Okay.
sometimes pushing it into a superconducting state.
So it's like taking a lump of coal and transforming it into a diamond, except instead of sparkling gems, we're getting superconductivity.
That's a good analogy.
What kind of materials can withstand these mind-boggling pressures and emerge as superconductors?
One of the most promising candidates is hydrogen sulfide.
Hydrogen sulfide.
You might know it as the compound that gives rotten eggs their distinctive aroma.
Wait, so the secret to room temperature superconductivity might be hiding in rotten eggs. That's both disgusting and amazing.
It is kind of ironic, isn't it?
But how does squeezing this smelly gas turn it into a superconductor?
Well, under immense pressure, hydrogen sulfide undergoes a remarkable transformation.
Okay.
It transitions from a gas to a liquid and then to a solid, ultimately becoming a metallic state.
Hmm.
And in this metallic state, it exhibits superconductivity at a surprisingly high temperature of 203 Kelvin.
Okay, that's still pretty chilly, but it's a huge leap forward from those cryogenic temperatures we were talking about earlier.
It is.
So hydrogen sulfide became the poster child for high-pressure superconductivity.
It certainly sparked a wave of excitement and research.
Right.
Scientists realized that hydrogen, the lightest element, played a crucial role in this high-pressure phenomenon.
Okay.
They started exploring other hydrogen-rich compounds called hydrides,
Hydrides.
hoping to find materials that could superconduct at even higher temperatures.
So hydrogen is the magic ingredient in this high-pressure recipe for superconductivity. What's so special about it?
Well, hydrogen atoms are incredibly lightweight and can vibrate very quickly.
Okay.
These vibrations, called phonons,
Valence.
play a crucial role in mediating electron pairing, the key to superconductivity. It's like those synchronized electron dancers, the Cooper pairs, needing a fast-paced beat to keep them moving in perfect harmony.
So hydrogen's rapid vibrations provide the rhythm for this superconducting dance.
Exactly.
And did scientists find any other hydrides that could outshine hydrogen sulfide?
They did. In 2020, a team of researchers made a groundbreaking discovery.
Okay.
They found that a carbon-sulfur-hydrogen compound, when squeezed to an astounding 267 gigapascals,
267 gigapascals.
exhibited superconductivity at 287 Kelvin.
Hold on. 287 Kelvin, it's about 14 degrees Celsius, warmer than a spring day.
It is.
We're talking actual room temperature superconductivity.
We are.
This is huge.
It was a major breakthrough.
But there's got to be a catch, right?
There is the pressure needed to achieve this room temperature. Superconductivity is still incredibly high.
Okay.
It's like trying to recreate the conditions at the center of the Earth, not exactly practical for everyday use.
Okay. That's a bit of a buzzkill. So we've climbed Mount Everest, but now we need to figure out how to build a city up there.
A good way to put it.
What are scientists doing to overcome this pressure hurdle?
They're exploring a few promising avenues. One is to search for materials that can exhibit room temperature superconductivity at ambient pressure. Without the need for all that squeezing, it's a challenging task.
Right.
But there have been some intriguing leads with researchers investigating new families of materials like nickelates and organic superconductors.
So it's like a global treasure hunt? With scientists from different disciplines joining forces to find that elusive room temperature ambient pressure superconductor.
Exactly.
What are some of the other strategies they're pursuing?
Another approach is to focus on metastable states.
Metastable states.
Imagine taking a high-pressure material that exhibits superconductivity and then finding a way to freeze it in that state even after the pressure is released.
It's like capturing a lightning bolt in a bottle, preserving that incredible energy.
That's a great analogy.
Is that even possible?
It's a very active area of research, and scientists are making progress. They're exploring techniques like chemical doping, where they introduce impurities into the material to stabilize the metastable superconducting state.
Okay.
They're also experimenting with thin film deposition, creating ultra-thin layers of the material to enhance its stability.
So it's a delicate dance between pressure composition and structure,
Yeah.
trying to coax these materials into revealing their superconducting secrets at room temperature.
Yes.
And what if they succeed? What kind of world could we create with room temperature superconductors?
It's a question that sparks the imagination.
Yeah.
Imagine a world with lossless power grids where energy is transmitted across continents with near-perfect efficiency.
Okay.
Picture levitating trains gliding silently at incredible speeds,
Right.
revolutionizing transportation.
Wow.
Think about medical imaging becoming more affordable and accessible,
Yeah.
leading to earlier diagnoses and better healthcare outcomes.
And what about computing?
Oh, absolutely. They could pave the way for faster, more energy-efficient computers,
Hmm.
ushering in a new era of technological innovation.
Right.
And they could even unlock the potential of quantum computing, leading to breakthroughs in fields like medicine materials, science, and artificial intelligence.
This is mind-blowing. It's like we're standing on the threshold of a technological renaissance,
It really is.
powered by the magic of room temperature superconductivity.
Mm.
But as we've seen throughout this deep dive, superconductivity is a field that constantly challenges our expectations. What are some of the hurdles we might face as we enter this new era?
One of the biggest challenges is scalability. Even if we discover a room temperature superconductor at ambient pressure,
Right.
producing it on a large scale and integrating it into existing technologies will be a monumental undertaking.
It's like having the blueprint for a revolutionary invention, but needing to build the factory and the infrastructure to make it a reality.
Exactly.
What about the economic and societal implications?
Those are crucial considerations as well.
Mm.
How do we ensure that the benefits of this technology are shared equitably?
Right.
What are the potential environmental impacts? These are questions that need to be carefully addressed as we navigate this uncharted territory.
It's a reminder that even the most groundbreaking scientific discoveries come with responsibilities.
They do.
But despite the challenges, the future of superconductivity is incredibly exciting.
Absolutely.
It's a field that continues to push the boundaries of what we thought was possible, offering a glimpse into a world transformed by the power of zero resistance. It's a testament to human curiosity, ingenuity, and collaboration.
Yeah.
From that serendipitous discovery in a cold laboratory in 1911 to the relentless pursuit of room temperature superconductivity today, this field embodies the spirit of scientific exploration, and who knows what incredible discoveries await us in the years to come.
Who knows?
That's the beauty of science, isn't it?
It is.
It's a journey of endless possibilities, driven by our desire to understand the world around us and to harness its secrets for the betterment of humanity. Thanks for joining us on this deep dive into the fascinating world of superconductivity. Until next time, keep exploring.